crunch one in waiting.
Okay.
Thank you. Welcome everyone. It's a pleasure for me to introduce Juan, as we have been lucky that he has been sharing with us a year of his sabbatical with us. Juan originally is from Spain. He's been working in the University of Murcia for a couple of decades, probably. Specialized in technology that has to do with sensing, but also a lot of artificial intelligence expertise, especially in learning, and has a lot of interaction with companies over there, to the extent that he decided to create a spin-off as well, I think. And so today we have a glance of only one of his dimensions of expertise. So, Juan?
Thank you for the introduction.
What is the period is here?
Pardon?
Right here last September, and I will leave Middlesex this month. So I'm about to finish. I will keep working in London for at least a year more. But yeah,
You mean you will come back?
yeah, because I love the city. So thank you for the introduction. And the first thing that I wanted to say is that I'm very grateful for Middlesex University and Juan Carlos for inviting me here. It has been a really interesting period of my working career, and this is what I'm very grateful for to this university. I come from the University of Murcia, Juan Carlos said, and my talk will be centered in a work we have been developing in the last couple of years about indoor location using mainly smartphones. I will introduce my university context and my research group, what we do there. I will introduce also the general problem of location. We will focus afterwards in indoor location. What do we do within indoor location regarding this RSSI modeling, which is the part of indoor location we are working in. More specifically, we are going to speak about fingerprinting. Then, how do we materialize this in a concrete technology, which is the lock system and some compressors. My university is located here in the southeast of Spain. It's a small town, Murcia. For those of you that don't know, Murcia is near Alicante. Surely you know Alicante. And University of Murcia is a mid-sized university. It has two main campus. I'm located in this faculty here in the more technically oriented campus outside of the city. It's very convenient to access there through this highway. And why I'm doing this? Because we have the opportunity, thanks to Juan Carlos and the Middlesex University, to set up an Erasmus program. So we can exchange both students and professors between both universities. So in the case that you are interested in going to Murcia, you will work with me this campus and this campus.
How does one get there?
Sorry?
How does one get there? Where do you fly?
You take a flight from Luton directly to Murcia. So it's a couple of hours and a half, and it's actually very convenient, very cheap to go there. And some figures about the university, about the students: 116 basic grades, 53 PhD programs, 68 master studies. These are rough numbers, okay? A community of people, about 33 students. I said already the other day that Middlesex University is teaching 40,000 students, so more or less they have a similar size. We are this number of teaching staff, and also this all member of management staff. I mentioned here that we have Erasmus modules just created with Middlesex University. We have also, obviously, as many universities in Spain, we have programs with Latin American universities, mobility among Spanish universities, and also some programs with Asia, which is not the most frequent. And my computer science faculty is this nice building. It's very strange at the first moment, but it's convenient, comfortable. It's like a Faraday cage. It tries to resemble this. So it's very, very nice when you are trying to set up an indoor location service within this faculty. It's very interesting. And we have these four departments: information engineering and communications, which I belong to, languages and programming, computer architectures, more devoted to hardware, and applied mathematics, working on aspects like, for example, security and so on. About 100 professors, 1,000 students or more this year, and these are the studies we are offering right now. I'm more linked with ubiquitous computing, which is a part of a master studies there. Also, the way we are creating a master of science in big data and a master of science in bioinformatics right now. My research group is one of the largest groups within the university. It's the most important one in terms of scientific production and also in funding attraction in terms of either public and private funding. The coordinator of the group is Antonio Escarmeta. Antonio Escarmeta is more devoted to technologies related with Internet of Things. But this, for example, it has been his supervisor many, many years ago. These are the numbers around members. It's a mid-sized research group. We have active presence in Europe, also in national projects, and a very high-level technology transfer to Spanish companies. So we are a group of high activity in terms of research. Okay, so this is the introduction to my university. Now I will start. How many minutes I have for? When should I finish the presentation? Around 4, okay. Yeah. So the general problem of location. How do we understand the general problem of location? What is the context? We are working on location because one of the main areas of our research is intelligent environments. And in intelligent environment, you have an important problem, which is context awareness. Context awareness is a means to provide information about what is happening in the environment, what is happening with the user, what is the situation of the user. So the intelligent environment can adapt to the user and offers services which are pertaining to the current situation. Not only about what the user is doing, but also in terms of what are the available resources, what are the devices that the user can use, and so on. So location information is a key to enable context-aware computing, because in order to provide technology that the intelligent environment can use to adapt to the user, it should know where the user is located at in each moment. So this is something like rather obvious. So as true intelligent environments must be context-aware, true intelligent environment must be capable of managing some kind of location information. So this is the root motivation that lead us to work in indoor location. If we go to a general definition of location, we can use this one, which is a definition that I think is simple but includes all the necessary elements. Given a set of basic data we know about the environment, given also a mobile entity whose position is not known but some other observation, we are interested in obtaining the position of the mobile entity within the environment. This is sort of rather obvious, but for example, if we focus on some basic data we know about the environment, this basic data could be the structure of the building, a map. We can use to georeference a person, a device, this kind of information. This mobile entity is the entity that we need to locate. For example, in most of the cases, we are using some hardware to locate another hardware, but in some cases, we could be interested in locating, positioning users simply, and assuming that the user doesn't wear any hardware. So this is another interesting problem. We are also interested in obtaining the position of the mobile entity. This position could be geo-referenced or not. I mean, if we are talking about locating a person within a campus, within the campus, almost surely this position should be geo-referenced. But if we are trying to locate one person within a building, we don't need this geo-referenced information. We only need to say that this person is located in this room right now. The basic techniques, traditional classic techniques that we can borrow and use adapted to our technology are mainly triangulation and trilateration. With triangulation, basically, we play with the angles between landmarks and the mobile entity we want to locate. With trilateration, we are using information about the distance between the landmarks and the mobile entity we want to locate. So, as we need to focus on other aspects, I will skip basically this. These are the basic techniques we can use with radio frequency. Most of the most common technology that we can use in terms of signals exchanged between landmarks and mobile entities is radio frequency. So I will focus the discussion on radio frequency. But we can also use ultrasound, LEDs, infrared, cameras even. But I will focus on this because it's the most common technology, the technology that we are really focused on. We can use these approaches in terms of how do we use signals exchanged between receiver and emitter. We can use this approach, which is time of flight. We can try to measure what is the time elapsed between the emitter and the receiver when we exchange those signals. We can use the angle of arrival, which is belonging to this triangulation basic approach. We can use also signal extent. What is the level of the signal that arrives to the mobile entity, for example, and other useful signals that I already mentioned. In terms of using time of arrival, we have here a mobile entity that we want to locate. We have here a landmark, another landmark. So basically, we exchange signals between the two, and this landmark might be interested in measuring what is the distance. The distance, or estimating the distance between this point and this point, and this point and this same point. And estimating this distance can be done if we assume that the radio frequency signal is moving by the speed of light. Okay. So with these simple mathematical equations regarding to circles, we can estimate 2 points. By using 2 landmarks, we can estimate 2 points in which this mobile entity can be located at. And this second point can be discarded by using context information, additional context information, because we know positively that the point cannot be here at this moment. So in this case, synchronization is important because we need to measure what is the time elapsed between when we emit the signal and when the signal arrives. Okay, so depending within this same technology, in this case, we assume that synchronization is important between emitter and receiver because we need to share the same clock here and here in order to measure what is the time elapsed between since I emit the signal and the signals arrive here. Okay, this implies that the receiver has to, have expensive hardware in order to allow synchronization between emitter and receiver. But if we want to avoid this receiver having expensive hardware, which is, for example, the case in GPS, we can use time difference of arrival. Instead of measuring what is the time between the time that happens between when we emit the signal from the receiver and from the emitter and the receiver, we can use multiple emitters and measure the difference in times from these emitters to the receiver. So this implies that emitters must be synchronized between them. For example, satellites must be synchronized between them. But there is no need to synchronize the receiver. So this is included.
Sorry, do you assume synchronized clocks and all these?
Yeah, synchronized clocks in this particular technique only between emitters. In this case, for example, in GPS, you have to be synchronized. Your smartphone doesn't have to be synchronized with satellites, but the network of satellites must be synchronized with them. So this is interesting with respect to the other technique, because in this technique we need everything to be synchronized, even the receiver, even the smartphone in this case. Okay. An angle of arrival, what we are using as the main hardware technology is highly directional antennas. These antennas can measure what is the angle of receiving the signal, and we can play with these angles. Okay, but this normally requires more specialized hardware, which means more money and so on. And this is a technology that is actually not being too highly used, but it has been used by the American Army, for example, so on. So GPS technology is one example of time difference of arrival technology. All the satellites are synchronized between them. We have a receiver. This receiver receives signals from them, and the receiver tries to estimate the time difference between all the signals coming from the satellite. Okay? So with this time difference, we can throw these imaginary spheres, and by using simple mathematical equations, we can determine with some degree of accuracy the position of the mobile entity. Okay. Okay. With GPS technology, we need to see in the open air directly in a straight line 4 satellites in order to appropriately construct the position of the mobile entity. And after 2000, this signal was no longer degraded by the source. I mean, when the Americans through the DARPA initiative started to use this kind of satellites, they artificially induce some noise in the signal, so they can filter appropriately what are the users that get them the highest precision by using these satellites. Since 2000, this May 2000s, this signal is no longer manipulated, so everyone can use the same quality of GPS signal. There are clear limits of GPS technology. A GPS receiver device needs to see at least 4 satellites in the open air. This is a very important restriction. But in our spaces show a high variability in structure. It means first that we are not seeing the 4 satellites, nevermore. But also, if we were able to see the satellites, we are within a building, and this building has a very high variable structure, and this structure will affect the signal or how the signal comes to us from the satellites, because there are many different kinds of reflection and refraction surfaces within a building. And there is also a multipath signal propagation problem, which means that the same signal will come to you from many different places. And also the error distance of GPS at indoor environments is bigger than the room that we need to locate the user. Also, there is a time to first fix problem, which is the time that we need for the device to awake and start using GPS properly. That is partially solved by this technology, by using Wi-Fi and internet in order to exchange data between satellites and the device. But the problem is that GPS is not useful in indoor environments. It's clear because you will see the satellites, and also there is many complicated structures within the building that will prevent us to use these signals properly. Okay. So these are the basics, or at least I pretend that they were the basics of general location, what we have in indoor location. Indoor positioning, we want to situate the mobile entity or user within because it doesn't necessarily have to be a user. Because, for example, we could be interested in locating, goods within a fabric or within a common space in which robots are moving, for example. Situating the mobile entity and user within an indoor space by indicating position, and also nice to have would be orientation and direction of movement. But in many cases, they are actually not necessary. An indoor positioning system is the system, the infrastructure that we need in order to provide the necessary signals and mechanisms to construct the information that we need, which is where the device is located at. This indoor positioning system is based on landmarks, as the GPS is based on network satellites. We will use here also landmarks with either known or fixed position. This is important because in some of the technologies, we don't even know, we don't even need to know where the landmarks are located, as we will see later. And this EPS can actually locate tags. These tags are supposed to be the minimum hardware that is attached to the entity that we want to locate at. And also, they can provide the required sensing context for the device to locate themselves. So we have to distinguish between two systems. One system that the infrastructure is capable of locating the mobile entity, and other system that there is the mobile entity which is in charge of locating itself. Okay. If we think of location about as a service, what are the requirements we need to provide to construct this kind of service? This is very important because the requirements can be variable depending on the scenario. Location information is not necessarily georeferencing that we also previously mentioned. It can be of Boolean nature. For example, if we are trying to build a present service, we need to define a service that says that this person is present in this room or not. So we only are managing Boolean information of Boolean nature, or in some scenarios we will need room level granularity. Okay. We would use usually bidimensional information. I mean bidimensional information in a plane, but depending on the building, we could be also interested in locating people in different floors. So this set component will be a discrete value, not a continuous value. Positioning does not necessarily imply orientation or direction, and usually high response time is needed. For example, if we are trying to track an object, this tracking could be also reached. A good tracking service could only be reached if we have high response time. One problem is location. Location is positioning one object within a space, but over this basic information, we can also make tracking. Because tracking is when we are constructing the trajectory of the object to the building. And in some cases, for many applications, it's more important tracking than the basic positioning. So tracking is like a high-level service we built on top of the basic positioning service. So in tracking, we are interested in object dynamic trajectory to, for example, predict the object's location at time t prime, use the follow path to records and accounting. For example, if our tarification system depends on how the common space is used, this tracking service can be used in order to quantify what is the level of usage of our space. Think, for example, on an airport, on a mall, etc., in which it is important what is the number of people that goes through the door of your shop. Because you can use this information in order to offer, for example, you can balance the rent you are imposing a concrete shop with respect to other, if the place that the shop is renting is better than other one. Because you can demonstrate that many people is passing through your door and less people is passing through your door. So you can balance the rent that you are applying for each different shop. For retailing, you can use this for retailing, for modeling your behavior as a movement profile, and so on. So tracking is more about trajectories than about highly accurate location at any time. So tracking is another problem in itself, and we will focus only on location in indoor environments. If we are speaking about how do we use radio frequency for locating devices within an indoor environment, we can ask ourselves, which device can I locate in this kind of environment using radio frequency? We can locate Wi-Fi devices with computing capabilities, for example, smartphones, tablets, laptops, or mini PCs, Arduino, Raspberry Pi, and so on. We can also use Bluetooth We can also use RFID technology. We can also use side-beam modules and any commercial tags from commercial products using radio frequency technology. So, in terms of the sensorial infrastructure we need, and depending on the kind of device we want to locate, if we are talking about Wi-Fi, we would use a network of fixed and mobile Wi-Fi access point and routers. For example, this is the case that we are speaking later on. We are using a network of Wi-Fi routers deployed, and because actually nowadays they are actually ubiquitous. You can find access point in virtually any device in any building right now. And even if this building is not owning any access point, the rest of the buildings will do. So you can use the signal of access point from the rest of buildings surrounding your own one to position your devices within your building. Also, we can use a network of fixed Bluetooth devices, RFID antennas. These are very expensive, so maybe it's just not a very good idea to use them for locating normal users or devices. Adult networks of safety modes in order to high precision location of modes, because with this technology, using radio frequency, it is obvious that as many the higher the number of landmarks we use, the higher the precision that we will get locating devices. This kind of technology is very interesting because sailing modes are very, very cheap. But we have to take into account that we have to manage how to take care of batteries. Okay, all of them are wireless. Okay, I will skip these slides and go directly to how do we use in radio frequency the notion of signal strength as the basic matter to provide location. Okay. For example, within Wi-Fi devices, if we are scanning a network, we can receive the signal strength of the access point that are surrounding us. This basic signal strength at the end is an integer. It's an integer between -100 and 0 dB. We can use this as a signal strength measure. In terms of, if we are receiving a number proximum to 0, we are receiving a very good signal. If we are receiving a number with many dBs, minus or near to -100 dBs, we are receiving a very good bad quality signal. So if we use this main idea, how can we use this basic information to provide some kind of means for detecting the user? Because, for example, here we see this heat map. In this heat map, we are seeing different levels of quality of signal. This is the better one. So the access points should be located here. And here you see that it's clear that the variation in signal strength strongly depends on the architecture and also the materials within the building. So it's not linear, and we cannot easily create a basic mathematical model to predict, given that the access point is here, what is the signal I will receive here, because this is the basic problem that we have here. So if we want to follow this approach, we can follow it because it's very easy. We can use a very simple mathematical formula, which basically depends on the obstacles and the distance between the access point and the element, and we can obtain this estimate. And this is what we do when we are doing RSSI modeling. RSSI is how do we call this measure that we obtain by using the Wi-Fi signal when we are trying to measure the strength of the signal we receive. If we instead of this, if we are not interested in applying theoretical models of how the signal propagates through the environment, we can use this finger thing. If you look at here, for example, if we situate here, and if there are more than one access point here, we can measure at this point what are the access points that I am receiving. And for each access point, I can record what is the signal strength for this access point. So if I do a careful survey along all the building, measuring this, I can construct something like a map of signal strength, and I can use this map in order to build a fingerprinting of the signal within the building. If I relate each lecture of RSSI signal with where I took the signal, this fingerprinting map can be used as source data in order to build a model that allows me to locate people within buildings. If we are talking about RSSI modeling, we are, for example, if we are in a concrete position, we can, for example, detect this MAC address corresponding to different access points. These are the channels through through which the signal is emitted. These are examples of signal strength. This is of very bad quality, but maybe it could be also a valid data to position, and this is the timestamp. Okay, so we can use this in order to model it by using the RSSI of the 3 access point and also the location of the 3 access point. We can elaborate a trilateration model in order to estimate where are we now. Okay, this is the basic approach. The problem is that when we need to model how this value evolves through propagation through the building, this model, the theoretical model that we use, will never be so complex to include all the variables and all the factors regarding the structure, regarding the materials, and so on, to provide a good estimate of the distance between the access point, which is behaving as a landmark, and all devices. Okay? So this is, in principle, a good idea. We can build this kind of classical trilateration in order to estimate by using RSSI signal the distance between the point and the landmark, if these are access points, but the model will be affected by reflection, obstruction, and signal fading. And the signal will be noise by nature. You can see here that we can, this is a very simple scanning software in which we can use to see what are the Wi-Fi's that we are receiving right now. These are a list of Wi-Fi's, and this is the evolution of the signal in terms of dBs through time. You can see here that the high variability of signal is very unstable. We can use simple improvements for this, but this improvement will not reach the necessary quality to build a very stable location service. For example, we can use a combination of various access points, but highly weighting the nearest one, and assign to the mobile node the same floor, for example, which is something like a very simple fix. And we can also do more work on theoretical models for signal propagation. Actually, there are some projects right now at the European level that are trying to model this in a more precise way, in order to because the model that we have right now are very simplistic, doesn't take into account many factors, and these projects are trying to work on this. So let's see what happens in a couple of years or 4 years. This was about using RSSI by modeling the signal. But if we use the idea of building the fingerprinting map, how can we use this? Imagine that we have this fingerprinting map as a database of readings in which I made this survey moving through the building and registering when I'm here right now, registering what are the RSSI of the different access points I'm receiving right now, and each of these lectures is composed by different RSSI registers and a label indicating the location. Okay, so if I am able to construct this kind of database, I can use machine learning in order to try to approximate where the users is located at. For example, if I can use for example, construct a neural network capable of learning in terms of RSSI lectures or readings, predict a label saying where the user is located at, in terms of, for example, this CED setting room, I can build a very simple service locating indoor location service with this. Also, it is interesting to know that access point location might be not known beforehand. When we are working with signal modeling, we necessarily need to know where are the access points, because this is a basic information. But if we use machine learning, we do not need even to know where are the access points located. In this case, for example, I can build a location service without without knowing where are the access points. I simply scan through the whole building, construct a database with this, and try to construct, for example, a neural network, a decision tree, or any kind of classifier to predict where the user is located at, depending on the lectures. Okay, so if we see this as a classification problem, it's about learning a function, taking values in Rn, which means that we are obtaining values of the different RSSI strengths that we are perceiving from the environment, and we generate different locations as output. Okay? We can see this also as a regression problem, in which instead of saying that the user is located in this room, I can also say that the user is located in this room, but in a concrete position of this room, obviously with some kind of error. Okay? So in a regression problem, we are taking the same inputs as in this problem, but we are, instead of generating labels as an output, we are generating points in 2 dimensions. Okay?
XR is the real numbers.
Yeah, real numbers.
Okay.
Yeah.
So but you
and dimensions in real numbers.
Are you kind of use a discrete model of real numbers?
Yeah, in the case of decibels, yeah. It could be more correct to say n here for natural numbers. Yeah.
Because that's what you're only interested in. You don't really need to precise position.
Yeah, right. Okay. So there are 2 variants for this. The first variant is no infrastructure. We don't need to know in advance where are the access points. So we use this kind of guides to make site serving. They use, for example, a tablet to move through the building, scan, saying, now I'm here, start scanning, now I'm there, start scanning. So I construct a database through Surrey. This database is moved to a data analysis server. This server is in charge of creating the machine learning model, the prediction machine learning model, either a classifier or a regression model. And once that this model is created and validated, and we have tested that it has reached the required quality, we pass this model to a web service. And once the model is within a web server, we can use clients, because this client will have similar devices making a similar scan operation, and when they scan, they will send the scan to the model, and the model can predict where the user is located. Okay? So in this no-infrastructure version of the technology, we don't need to know about the access point. We don't care about them, and we easily build this kind of model by using this rather complex site serving. Okay? There is another variant, which is infrastructure-based. In this variant, we own the access points. We some kind of modify the access points by adding some sniffing code, in which we are interested in for any Wi-Fi device which is emitting packets, in order to see which are the Wi-Fi networks available. We log all these packets. We log the RSSI value of the intensity of the signal emitted by each device, and we use this information for location. How are we able to use this information for location? Because previously, as we did here, we are also making a site survey, the same kind of site survey. But in this case, the site survey it's composed by the level of RSSI values perceived by the access point, not perceived by the mobile. Okay? This is the only difference. In this case, obviously, we need to own the access point, and the features are different. In this case, in the first case, obviously here, in order to locate these users, we need to install additional software. They need to be aware and manage and allow to hold a simple scanning software so they can be localized. In this case, not, because in the extreme case, they will not even aware that they can be localized, because any Wi-Fi device is continuously emitting packets to see what are the networks available. So we can use these packets to provide location for these devices. I'm not talking about privacy issues and so on. This is something arguable, okay? I'm talking about which this is possible. It's possible relatively. For example, Apple is aware of this problem. They from the very beginning, they wanted to control how their devices are located. For example, here, when you are scanning by using an Android phone, it's okay because the Android's browsing system lets you make the separation. But if you are using iOS, iOS doesn't let you invoke the necessary API for scanning the Wi-Fi. So you cannot implement these mechanisms in iPhone devices. But in this case, you can. But you can't until iOS 8 arrives. In iOS 8, they are supposed to implement a mechanism in which when they are scanning the network to see what are the Wi-Fi available, they are using random MACs. Once they connect to a network, obviously they use their own MAC. But while they are only scanning, they're using random MACs, so this random MAC is not useful anymore for the access point to provide a concrete lecture, because you cannot associate the device with a random MAC with a concrete device with a real MAC. Okay. There is these two variants have a single common bootstrapping procedure. How do we build this system? We design the system either by designing a service strategy in the first case, or deciding how do we distribute the access point through the environment. Then we perform the survey. After performing the survey, if we have enough data, we generate the location model by training. We evaluate the model. If the model has the required quality, we deploy the model. If not, we again redesign this step and execute again. And we periodically repeat the process for getting some data and adding new survey. Why do we have to periodically repeat the process? Because the access point ecosystem will vary. They will not be fixed. Some will be broken, some will disappear eventually. Other new access points will come to play, and so on. If we talk about the specific results of this technology, for example, here we have just finished some kind of survey we are trying to, is under review now. And in this case, you can see here in this first table, what are the success rate in classification that we use when we are building a service for classifying, for locating people in concrete rooms, okay? So we are generating as the prediction a label corresponding to the room. These are different words. These are not us. So, for example, you can see here that apparently they reach a very good accuracy. For example, here this 97 means that 97% of the times they locate correctly the device. Okay. The technologies they use in terms of machine learning, for example, these are decision trees, Bayesian networks. These are it's fuzzy logic, KNN, bagging, decision trees, and so on. So many machine learning techniques and highly variable. It means that no machine learning technique is better than the others in these kind of problems. And instead, in terms of regression, you can also see here that instead of presenting accuracy in terms of percentage, they present the results in terms of meters, average meters in error in meters. Okay. For example, in This must be handled with care because any system use a different experimental setup. One use the laboratory, other use a living lab, other use a building, and so on. So this is not really comparable between them. There is an European initiative, which is the e-eval, which Juan Carlos is involved with them, that are trying to design a common framework in order to evaluate these technologies in the same conditions. So you can hopefully determine which is the best technology in a very concrete scenario. Okay, so these results must be handled with care. But it seems that they are very reasonable results. For example, here with a random forest, which is for us is the technique that always overcomes the other. We have a more than reasonable 78.45% of hits. And the environment is this. We have a two-floor house in which, for example, in the case of classification, this is the outline, the outline of the layout, sorry, of the house. And this is the same house, but here, as we are doing regression, we need to design what are the points for doing the site survey. So you create a grid, an imaginary grid along the house, and you use these points to position and scan. Use these points to be there, scan the network, move to the other point, scan the network, and one point after the other. Okay. In terms of infrastructure, here with the same setup, a house of a two-story house, we collocate sniffers strategically distributed around the house, and the results are reasonably good. With 7 sniffers here, 2 floors. This is the only experiment so far we have found that it was experimenting in different floors. These other ones we found in the literature address only 1 floor, and we obtained an average error of this is the one for regression, and this is the one for classification. For classification, we are reaching this reasonable value, and for regression, we are reaching this best among all of them mean error in terms of distance. So, improvements. This is a basic setup, okay? But many improvements can be done. For example, we can carefully look at the data before passing the data to the machine learning model, pre-processing. For example, deciding which are the access points that we should use for learning, by using, for example, feature selection. And we are working now in this idea in order to, instead of using particular atomic readings of the environments, we could transform a reading of 10 seconds in a time series and use this time series as the tuple for learning. I think this approach will give us very good results, but we don't know yet. For post-processing, we can, instead of working on pre-processing, we can also work after the prediction is done, because we can reconstruct the trajectory of the user. And if we know that some trajectories are possible and others are not possible, we can use this information in order to fix possible error-free trajectory by using a priori knowledge and historical data. And we can also obviously add more sensors, accelerometer, gyroscope, compass. There's many literature we can find about this, but adding more sensors prevents you to build a product which is used by everyone, because you are adding complexity and more technology and so on. So I will present the log system. The log system is the materialization of this technology in a concrete product, in which we have the same setting. Here we have, for example, if you are thinking about a mall, the mall has an owner, the mall has some tenants, for example, renting some space in order to put their shop. SARA, and so on. And you have a backend system which is logging all the readings from the mobile devices of the people that which are the customers of this space, and you create whatever you want to create with this information. Okay, we provide only the infrastructure, the network software in this case here in the backend, and the software in the Android phones. Okay, we use a web-based application in order to build the system, because we need to visually represent the system, and this visual representation is transformed into a graph which goes into the mobile application. This mobile application can be used to make the survey, and with this survey we can create the database. With the database we can create the models, and with the models and this graphical representation we build here, we can test the models, make some demos, and so on. This is the basic approach. Okay, and also the model will be in a web services, which is widely accessible, and we can manage in the backend many different models for many different installations. And the business model here is based on tarifying by access to the service. Okay, this is the main idea. So the business of indoor positioning is very important right now. It's growing in importance. There are some predictions that say that the business volume prediction will be between 2.5 and 4 billions for 2018. There are some strategic movements by companies. For example, Apple buys the last year Wi-Fi slam in early 2013. Google Indoor Services being more accurate and more extended. For example, you can use this Google Indoor Services in Harrods here, in London, and so on, many different places. There is an Indoor Alliance, which is a consortium of many different companies, very important companies, Microsoft, Cisco, Intel. The main ones, Google and Apple, they are not there. So this is not unusual. And mainly they are focused on using Bluetooth and Wi-Fi. And we can find many examples of real application, mainly in retailing, in malls, airports, museums, and so on. And to conclude, indoor technology is reaching maturity now. Plenty of technologies and techniques. We have been focused only on Wi-Fi fingerprinting, which is the one that we are using. Machine learning and computational intelligence can be very useful here. And most of them are based on radio frequency, but you can use many other different sensors, for example, light from LEDs, ultrasound, infrared solutions, and so on. So these are the references, and thank you.
Any questions?
How good does it handle if the environment itself changes? So, for example, there is, I don't know, a mobile stand of some kind, and it's moving through the environment. Obviously, it's changing the signal strength of the different hotspots. So, would this mess up?
Moving in terms of what, for example?
Like, I don't know, a mobile shop. So not for mobile devices, but like the shop itself is mobile in a mall, just as an example. Something which is moving around, or maybe you have crowds of people in one room, which is obviously somehow changing the signal strength in that room.
Yeah,
so,
yeah. The key, I didn't say that, but this site survey is not done once. In order to our experience is that you need 4 or 5 days to make this site survey. You start doing 1 hour Monday, 1 hour Tuesday, and so on. So you cover all the week. You create a database with readings from all the week, and then if you process it accordingly, you will select only the access points that are seen all the time.
Okay.
So in this case, you are more or less discarding this kind of mobile settings. The downside of this is that you cannot build the system immediately. You will need a week or 3-4 days in order to build it with enough accuracy.
So
to start working.
Because if I understood you right, then you basically during this process over a week, you're basically getting all the different scenarios that might happen during this time.
Yeah.
Okay.
This is the idea.
Okay.
independent, for example, in a university, it's a good approach is to do it from Monday to Friday. But in a mall, it's a very good approach to do it from Wednesday, for example, to Sunday.
All right.
Because there is a high activity during the weekend.
All right.
But more than some of the scenarios, I think is about detecting which places are statistically more consistent. You don't understand what's going on in the place. You just understand signal strength statistically over time.
Yeah, in this case, you are right. Machine learning is oriented to that. Machine learning is trying to find patterns, regular patterns that repeat during time, so you can use them to decide. But it's up to the neural network or to the decision tree to find it.
And the more often you do it, the more robust is the training, and the more predictable the output. Any questions?
Should we play?
Yeah, interesting.
Would you use any of the signals, any of your repeaters, for example, to detect the signals of the others, like temporarily instead of being on full power and be transmitting, then all of a sudden you use them as if they were detecting?
Can you rephrase the question?
Any of your transmitters can be a receiver.
Yeah.
If temporarily you just disable it from being a transmitter and detect it and let it be aware of all the rest of the transmitters as a auto-referencing and auto-sensing the signals, then at least you can accelerate the learning process and also be far more accurate because you're always as near as possible, checking the signal, just in case if somebody decides, I don't know, let's say to throw his jacket on top of your transmitter, and for whatever reason he had some metallic object, and your transmitter now from signal strength being, let's say, maximum, it drops down to minimum. Now, even if you were relying on it, that means the rest of the data will never be there. But if any of each one of your transmitters momentarily pauses from transmitting, just chooses to receive for a short while, detect it, let it be aware of the signal, the remaining signals around it, and then carry on transmitting and feed that data back, then you'll know to start ignoring the one that's been disabled accidentally and move on. And keep to improve your accuracy. And you can keep that as an active process, like once every hour or once every whatever. Just stop transmitting.
How do you decide when you change?
You can just throw it as a random sequence. It matters not. All it's doing, like for example, if you have A, B, C, D, A momentarily pauses transmitting. Just let it be aware of B, C, and D, and if there's any additional one somehow which might have appeared, then carries on transmitting as A itself and moving on to the next one and so on. And then all of a sudden you're not only aware of newer signals to be added, but you can decide to ignore the signals from A, assuming that it was disabled accidentally or intentionally. Whether it was sabotage or just accidentally, as I said, somebody throwing a jacket next to it.
Yeah, it's some kind of a strategy to work. Yeah, when you need high availability.
Not only that, it will be the learning process will be quicker because rather than you having to literally move, let's say, with an iPad or something around to detect the signals, you use the fixed location of the transmitters that you have to be knowledgeable of the remaining transmitters at the expense of what, 1 second in, let's say, a minute in an hour.
Yeah, but in the first scenario, you don't know even that.
No, but that's when the rest of it will be learned process. But then at least it won't matter if any of your transmitters fails. You can carry on with the remainder. But at least you will try to clone the failed one, just in case if it goes back to life, then you can carry on with its data.
In the scenarios we worked, for example, in malls, in the university, we didn't find this problem actually.
It also depends on where you've located them as well.
Yeah. The kind of networks we found were very stable, actually. So, but this is a very good improvement. Thank you.
No questions? Well, thank you then, Juan.
And next seminar? Do we know when the next seminar is?
Not really. No.
Not yet.
Again, we'll slow down for the summer, I think.
Is this the last one?
Okay. But we'll put the details on Twitter.
So, I mean, I don't know.
In the short future.
Will you
Sorry?
send me the
The short
details of the,
In the-
or I suppose I can fund them and
Yeah? Send it to you right now.
Yeah.